All right, let's get right into it. As a chief systems engineer, my world for the past 2 decades has been about solving what feels like impossible problems in the auto industry. And today, I want to pull back the curtain and show you the actual blueprint for how we crack one of the toughest nuts out there.
So what is that puzzle? You might think it's about building the fastest hypercar or the most luxurious sedan, but nope, that's not it. The real challenge, the one that actually impacts millions of people, is this. How do you engineer an electric vehicle that is genuinely safe, but that almost anyone can afford? It's really about democratizing safety, making it accessible for everyone. And that right there brings us to the absolute heart of the problem. We call it the cost safety paradox. Think about it. On one hand, you've got this incredible pressure, a vehicle price under $10,000. Every single part is under a microscope. But on the other hand, you have this brick wall of global safety standards. And these are non-negotiable, just as tough as the ones for a $60,000 SUV. Failure is just not an option. So, how in the world do you solve that? Well, I'm going to give you the answer right up front. The core, the absolute foundation of our entire engineering spec is something we call a lean, high-voltage architecture. Now, let's be clear, this is not about cutting corners. Not at all. It's about being smarter, making a strategic choice right from the get-go. So let's walk through this blueprint together. Okay, first things first. Before you can even think about designing a single wire, you've got to understand the rules of the game. And believe me, when it comes to these micro EVs, the rulebook has been totally rewritten. It's like navigating this global gauntlet of safety regulations that are now incredibly strict. What we're seeing is this incredible global convergence. You know these little low-speed vehicles? They used to live in this kind of regulatory gray zone. Well, those days are over. It doesn't matter if you're in Beijing, Brussels, or Washington, D.C. The standards are demanding the same high level of electrical safety across the board. And what that means for us as engineers is that we have to completely ditch the old, simple electrical systems. And look, if you want to point to one thing that really set this new global benchmark, it's China's GB 18384 standard from 2020. This thing, it's not just some minor update, it is a total game changer. It makes advanced features like active insulation monitoring mandatory. That's stuff that used to be only on high-end EVs. It has basically raised the bar and the cost of entry for anyone who wants to play in this space. 5 minutes. That number you see? It's not just a random number. It is literally a lifeline. The new standards say the battery system has to give people in the car at least a 5-minute warning before a thermal runaway. That's when a battery cell just goes critical and overheats. 5 minutes. Think about that. That's the difference between getting out safely and an absolute catastrophe. And that's the level of safety we now have to build into a car that costs less than 10 grand. Okay, so you've got these insane demands. How do you meet them? Well, to figure out the right way forward, we did what any good engineer does. You benchmark. You look at the market leaders. And when we did, we found two totally different approaches, two completely different engineering philosophies trying to solve the exact same problem. It's basically a tale of two cars, the Wuling Mini EV versus the Citroën Ami. All right, let's get into the nitty-gritty here. So you have Wuling. They went with a higher voltage system, somewhere between 96 and 144 volts. And their strategy? Absolutely brilliant. They decided to tap into the massive, already existing supply chain for regular passenger cars to get their costs down. Smart. Now Citroën, they took a different route. They stuck with a 48-volt system. Why? To stay just under that high voltage classification and kind of sidestep some of the tougher regulations. But, and this is a big but, that created a massive engineering headache. To get the power they needed at that low voltage, they had to pump huge amounts of current through the system. And that means thick, heavy, expensive copper wires and a real nightmare trying to manage all that heat. So for us, the analysis was crystal clear. The path Citroën took with the Army, look, it was clever, I'll give them that, but it's an evolutionary dead end in this market. The sweet spot, the absolute optimal architecture that balances cost, safety, and performance is right there in that 96 to 150 volt range. And that is the foundation of our entire lean blueprint. Okay, so we've got our strategy locked in. Now comes the fun part, translating that high-level strategy into the nuts and bolts engineering details that actually save lives. And we're going to start with one of the most critical safety systems in any electric vehicle, period. It's called the high voltage interlock loop, or HVIL for short. So what is it? The easiest way to think about the HVIL is like it's the high voltage system's own personal sentinel, or maybe a digital tripwire.
It's this simple, low-voltage circuit that makes it complete loop through every single high-voltage connection in the car. If any one of those connectors starts to come loose, even just a tiny bit, that loop is broken, and the HVIL is the very first thing to know about it. And this whole thing works on a really elegant principle called last mate, first break. It's super simple but incredibly effective. So check this out. An operator starts to unplug a high-voltage connector. The HVIL pins are designed to be just a little bit shorter, so they are the first thing to break contact. The instant that happens, the sentinel circuit is broken. That signal flies to the battery management system, which immediately commands the main contactors, think of them as giant safety switches, to open up and cut the power. All of this happens in milliseconds, so by the time the big main power pins actually separate, the high-voltage current is already gone. No power, no scary electric arc.
Okay, now here's a little detail that really separates the pros from the amateurs. In our spec, we don't just use a simple steady DC voltage for this HVIL circuit. No way. We specify a pulsating signal, what's called a pulse width modulated, or PWM signal. So why go to the extra trouble? Well, a simple DC circuit could be fooled. If a wire gets pinched and creates a short, the system might think the loop is still complete, when it is absolutely not. But a PWM signal is like a secret handshake. The system isn't just looking for a connection, it's looking for that very specific pulsating pattern, making it so much more robust. So we've got our architecture, we've got our smart design details, but there's one final piece to this puzzle. And honestly, this is the piece that makes that sub-$10,000 price tag even possible. It's not just about clever design, it's about making billion-dollar decisions in the supply chain. This chart really lays it all out. I mean, just look at the impact here. By going with our 96 to 150 volt platform instead of a traditional 400 volt one, bam, you slash component costs by 30%. By integrating things into one single power unit, you save another 15%. And my favorite one, the fuse. You swap out a $50 high-tech pyro fuse for a $5 ceramic fuse that does the job perfectly well. That's an 80% savings. See, this isn't about making things cheap, it's about being smart. The huge cost savings come from intelligent architecture and strategic sourcing, not from cutting corners on safety.
And that brings us to the where. Where do you get these parts? We specify that you have to prioritize the world-class domestic suppliers in China. Companies like Hongguang for contactors, Sinofuse for fuses. And let me be really clear, these are not some second-tier bargain bin companies. These are global leaders. They have achieved mind-boggling scale and incredible quality, specifically in this niche of micro-EV components. They are, quite frankly, the secret sauce that enables this entire strategy to work. So let's bring it all home. The most important takeaway here is that the paradox, it's solvable. By combining this lean 96 to 150 volt architecture with a laser-focused strategic supply chain, you absolutely can build a car that meets the toughest safety standards on the planet and still hits that magic sub-$10,000 price. Safety and affordability aren't enemies. They are the direct result of just plain excellent engineering. Now, this blueprint, it absolutely solves the paradox for today. But here's the thing about technology. The pace of change is relentless. This 150-volt system is the perfect, elegant solution for right now. But the question that keeps us up at night is, what does the next blueprint look like? What happens when new technologies make 800-volt systems just as cheap as this one? Well, that, my friends, is the next great engineering puzzle.